Hello, so our presentation is about curvature in general relativity. We're sort of just going to be going over curvature and then some of its effects and examples in quantum mechanics.
Before we get into how space-time curvature works and how it affects our reality, we need to introduce a thinking that turns into the general theory of relativity. Like most lectures and presentations on this topic, I would begin with Einstein's equivalence principle. Let us take one elevator and put it in space where no forces will have a significant impact on it. We then accelerate this elevator at a rate of g. Then let us take another identical elevator and put it on the surface of the Earth, with its gravitational field strength being g. Einstein theorized that if we were in either elevator, there would be no experiment we could do to tell the difference between the two situations. Thus, these two scenarios would be the same. Now, let us shine a beam of light in our elevator on Earth. It is assumed that light would follow a straight line. However, when we shine light in our accelerating elevator from the reference frame of the moving elevator, the light will curve downwards. This would violate our newfound equivalence principle, since we would have a situation where light curves and one where it doesn't. In order for this principle to be true, light must be bent by gravity. This brings up a new issue: how is light accelerated? Because light is massless, we cannot apply a force on it that would accelerate it. So it was always assumed that light would travel in straight lines. Straight lines are the shortest distance between 2 points, and in Einstein's theory, he claims that light is still in fact traveling in the shortest distance between 2 points, it's just that this straight line is now curved. Thus, light is not affected by acceleration. These lines created by curved spacetime are simply the paths it would take with no external force. This has consequences, including time dilation. Since our light path is no longer straight, the length of the line is greater. So to keep the constancy in speed of light, the time that it takes this light to travel will be longer. This can be given by a transformation for a proper time and a gravitational field. This is very similar to the time transformation with velocity in special relativity, since we are simply replacing our velocity squared with the acceleration due to Earth.
We're going to start off with the basic math section to sort of define curvature and what it means. Just as sort of a review from Calculus 3, curvature is just a measure of how much something deviates from being flat or straight. I don't think we really need to go through examples that much. But in math, which I'm going to spend a little more time on, is curvature is defined as the change in a vector if you take a step along something. For something perfectly straight, the change in the vector, I use the normal vector here, it has a ratio of 1 to the change in position. Basically, if you take a step, the vector doesn't change. And then on the second example, for something curvy, that's simply not true. If you take a step in position, the change in the vector does not equal 1. In this example, it would be greater than 1. And then as a final note, in practice, this is a differential element, the derivative of the vector in respect to arc length or position. But from Calculus 3, we need to extend this concept to space itself. And the way to do it is to just conceptualize space as a being about relative curves. So in the graph on the left, the grid lines being dx and dy, red and blue, and then the black grid lines, those are curves from another reference frame. So while maybe in that reference frame, the distance is defined normally, from a different reference frame, we have to add error correction functions in this second expression. These error correction functions are stored in an object called the metric tensor, which is basically a matrix representing what corrections you have to do based on what reference frame you're viewing the world from. In particular, curvy grid lines or reference frames that are accelerating, are going to have error correction functions that aren't linear. You're going to start having terms that basically mess, so to speak, with distance in any number of ways. In general relativity, the error correction functions correspond to curvature. This curvature object is called the Ricci/Riemann curvature tensor, and it's way more complicated than the curvature of simple curves. The same premise is true though. Instead of thinking about, the change in a vector along a curve, you have to start thinking about the change in a vector based off space. Almost like you're doing little circles around a point, and then you're asking, how does the vector change based off each rotation of the circle? In practice, it's about coordinate directions and taking a step this way and that way. But the objects storing the curvature tensor are the Christoffel symbols, the little gammas in this expression here. The Christoffel symbols are basically the equivalent of curvature of space. They describe the change in vectors based off change in direction. And the curvature is defined, the sort of net curvature of space is defined as a very complicated expression of these vector changing functions. That being said, there's a final concept here, that being geodesics. Geodesics are just lines on curved space. There are many different types of lines, but geodesics are basically paths that you follow in many respects. But the concept of a straight line starts to become blurred, because based on what coordinate frame or what coordinates you use, straight lines can mean vastly different things. The example I give here is polar versus Cartesian. A straight line in polar is very different than a straight line in Cartesian. That being said, we do have tools to connect these viewpoints, mainly the geodesic equation. The geodesic equation just describes that the acceleration along a coordinate direction, the change in a coordinate direction in respect to tau, or proper time, is equal to this component of curvature, one of the Christoffel symbols, times a product of velocities along different unit directions. And this equation is sort of the fundamental tool of general relativity. It's going to describe how planets move, how light behaves, and all sorts of things. But it is the tool that connects curvature with observable phenomena.
Curvature isn't caused by gravity. Gravity is curvature shaping movement. Quoted by John Wheeler in 2008, spacetime tells matter how to move, and matter tells spacetime how to curve. The idea behind curvature is that gravity does not exist at all. It is simply an illusion created by the curving of spacetime. This is the reason, as we talked about earlier, why light accelerates, or more accurately, why light curves when it is close to massive objects. Yet this brings up another question. How are forces balanced with an object being pulled by gravity? Traditionally, we would consider gravity a force, and a normal force resists that force of gravity. Consider an apple sitting on a table. In classical mechanics, the apple would have a zero net force, where the force of gravity cancels out the normal force. However, as we learned, gravity isn't a force, then there should be a non-zero force on an apple sitting on a table. And yes, that is true. That apple will feel a force due to the repulsion from the table, and it will be accelerating upwards. By the equivalence principle, this situation would be the same as if the apple was sitting in an elevator accelerating through space at g. If we were stationary relative to this elevator, we would see that elevator accelerating up and pushing on the apple. But by the equivalence principle, this is the same as the apple sitting on Earth's surface, so in reality, the Earth is accelerating upwards and creating an upwards force on the apple. Now let's consider the apple falling down, rather than it sitting on the table. This means that our apple is in free fall. Classically, there are no other forces on it but gravity. However, in general relativity, gravity isn't a force, but the curving of spacetime. So there are no other forces acting upon this object, and it must be experiencing no acceleration. We can consider this equation for an object's proper acceleration. In it, we have the change in velocity with respect to proper time. This is classically what we consider acceleration. Our other value is the gravitational acceleration, and this is what we can compare to an object's acceleration as a result of curvature. Both these values are equal to 9.8 meters per second squared. and then our two accelerations cancel out, leaving our proper acceleration at 0. Despite everything we know about gravity, general relativity isn't perfect. We don't know how gravity and general relativity behave in the quantum world. Let us consider the wave function of a small particle. This particle has mass and will curve space by a small amount. However, since we don't know the position of this particle, we can't find the curvature that it shapes. According to general relativity, mass warps space and time around the particle. Schrödinger's equation can't tolerate space and time warping in two different ways, in which the superposition would collapse. Thus, in general relativity, there is no way to make a superposition of curvature. And if we were to include relativistic transformations to the Schrödinger equation, including those of special relativity, it would remain incomplete. Let us apply spacetime curvature to a real-life scenario. Since spacetime is warped near massive objects, and these straight lines that light travels across are also warped, then we should be able to see light from an object that traditionally should be blocked by another in front of it. When general relativity was first proposed, skepticism arose. To prove their theory, scientists went on an expedition to Africa during a solar eclipse. The solar eclipse would hide some of the light coming from the sun so that they could see what lay next to it. This was called the Eddington experiment. After using certain instruments to look into the sky, they discovered certain stars next to the block sun. Scientists then returned around 6 months later, now that the Earth is on the other side of the sun. They now had found that those same stars were in a different position before. This is due to the curvature that the sun caused around it. Light from these stars had now bent, giving an appearance that it was in a position that it was not. Of course, this experiment didn't go flawlessly. Weather conditions and continued skepticism caused this expedition to reoccur multiple times.